Welcome to The Explainer. So glad you're here. Today, we're diving straight into a totally mind-bending journey, right to the absolute mathematical edges of light, mass, and honestly, physical reality itself. We're going to explore the underlying architecture of the universe, but we're not using abstract theories here, no. We're looking at the hard, precise mechanics of something called the dipole manifold. If you've ever wondered how the universe perfectly balances the weightless, instant zip of a photon with the crushing, heavy depth of gravity, well, you are exactly in the right place.
Here's our quick roadmap for today's explainer. We're going to cover the trig wall problem, the field of view equation, limit 1, which is the photon line, limit 2, the mass stack, and finally, we'll wrap up with the silver mean balance.
All right, let's kick things off with section 1, the trig wall problem. Computational bottleneck.
Okay, look at this definition of the trig wall. Now, standard physics relies super heavily on Euclidean radial normalization, right? Things like sine and cosine. But here's the catch. In high-velocity environments, using these transcendental approximations introduces this nasty thing called approximation drift. So instead of keeping a piece of data mathematically pure and perfectly discrete, continuous polar math effectively smears that exact identity across an irrational continuum. It's kind of like, imagine you're trying to precisely locate a single, sharp pixel on a screen, but your math just forces it to blur across 3 different pixels. That right there is the trig wall, and we desperately need a way to maintain bit-perfect identity without all that blurring.
That brings us to section 2. The field of view equation, the Seidel manifold.
Let's actually walk through the beautiful algebra of this field of view equation. Traditionally, the field of view is this somewhat clunky equation, A times the quantity 2b plus AD. But watch how elegantly this whole thing collapses under side A normalization. First, we set our side A unit constant so that A strictly equals 1. Because of this, the Pythagorean identity creates a perfectly rigid trade-off, a reciprocal identity where c minus b times c plus b equals exactly 1. Then we define the gap, c minus b, as our lens factor, which we call d. By substituting the math down, all those complex terms just beautifully collapse, and we arrive at a perfectly discrete total bounding rectangle for our field of view. It literally just becomes 1 by 1 over d. That's it.
So the absolutely crucial point here is this seemingly simple lens factor, d. It's our fundamental unit of resolution. I want you to think of d as the master dial on the universe's dashboard. By just turning this single dial, we control the very shape of our mathematical bounding box. And, as you're about to see, shifting this dial radically alters the physical realities of the universe.
Which leads us to section 3, limit 1, the photon line, the extreme flat limit.
Let's see what happens when we crank our mathematical dial to the first extreme. We're going to push the lens factor d right up towards exactly 1. This brilliantly illustrates what we call the squash effect. Remember, our bounding box is 1 by 1 over d, so as d approaches 1, the math is dead simple. 1 divided by 1 is 1. The vertical height of our field of view completely shrinks and collapses. What we're left with is a perfectly flat 1 by 1 box. Basically, it becomes a completely flat, non-decaying line limit.
So, what actually lives in this flat 1 by 1 limit? Light. This perfectly describes the linear, bit-perfect path of a photon. It represents a non-halting transverse vector with absolute zero drift in its trajectory. You know, in quantum electrodynamics, QED, Richard Feynman showed us that a photon explores all possible paths. But here, right in this flatline limit, destructive phase interference aggressively prunes away all those non-optimal chaotic paths. They mathematically cancel each other out to zero. So what's left? Just this perfectly clean, straight trajectory where the phase variation is stable. The photon doesn't pack any area, it just zips linearly straight across the grid.
Now for the exact opposite. Section 4, limit 2, the mass stack, the dense mass core. Notice the really sharp contrast here. On the left, we have limit 1, our flat 1 by 1 photon line. But on the right, if we hit the brakes and turn our master dial d all the way down towards 0, well, what happens to 1 divided by d? It blows up, right? The field compresses horizontally and stretches vertically into this hyper-narrow, infinitely tall strip. This right here is the vanishing area breakthrough. As we approach this limit 2 mass stack, we enter a really high decay power law zone. The space undergoes rapid area contraction and recursive nesting. It's essentially packing dense mass cores and data tightly inward, collapsing down toward a fixed physical boundary right at the center, which is known as the quark. So instead of falling into some uncomputable infinite void, you know, like a black hole singularity in continuous math, the path actually hits this quark. It's a terminal resolution floor. And this perfectly models how gravity and dense mass accumulate in localized state buckets. It's mind-blowing how well it fits.
So how does the universe handle this? Section 5. The silver mean balance. Resolving the tension.
Okay, we have a flat line limit for light and an infinitely deep stack limit for mass. How does the universe resolve this intense structural tension without just ripping itself apart? The answer is staring right at us. The silver ratio. Mathematically, it's when d equals the square root of 2 minus 1. Now, this isn't just a random number. This is the exact diamond equilibrium that balances the scales perfectly between those extreme limits of light and mass.
This silver main acts as a flawless, rational structural bridge. And what's super amazing is that at this specific resonance, a unit cell smoothly and perfectly decomposes into its own sublenses, with zero spatial approximation error. None. And hey, this isn't just some hyper-theoretical math trick. It actually governs the most stable structures in our real world. It's the exact proportion used to stabilize classical Japanese pagodas against earthquakes, safely distributing kinetic energy across the structure. It's even the exact ratio used in the ISO 216 A4 paper standard. That means every single time you fold a piece of A4 paper in half, it yields a bit-perfect, self-similar shard of the whole. How cool is that?
So to put it simply, and to quote the core concept directly here, the silver mean acts as the flawless, rational structural bridge, coordinating the photon's linear wave and mass's regional state buckets. It operates like a completely stable state machine for the universe. It perfectly coordinates the non-decaying wave vector of limit 1 with that area-packing mass accumulation of limit 2. And it does all of this without ever suffering from that messy trig wall approximation drift we talked about at the very beginning.
So I really want to leave you with this one provocative thought. When we look out at the cosmos, at the blinding speed of starlight and the crushing depth of black holes, are we simply witnessing the asymptotic limits of a perfectly rational, bit-perfect mathematical grid? The Side Manifold strongly suggests that yes, we just might be. Thank you so much for joining me for this explainer. I really hope this completely changed how you view the geometry of our universe. Keep exploring, keep questioning, and I'll catch you next time.